In this video, we're going to go over how to calculate pOH from the concentration of hydroxide. We're also going to go over how to calculate the concentration of hydroxide from pOH. And lastly, we're going to talk about how do we calculate pOH from pH or vice versa. Okay, so in an earlier lesson, we talked about calculating pH. And the important part about calculating pH is that you need to, or it is correlated with the concentration of hydronium ions. However, with pOH, that is correlated to the concentration of hydroxide ions. So that's an important note to make sure that you remember here. Okay, so same deal with this formula as with the pH, calculating pH from hydronium ion concentration formula. The trickiest thing for students to remember is the negative in front of the log, so don't forget that. Because if you do forget it, you're going to get weird numbers. Okay, now looking here, it's saying that, okay, the pOH scale is the reverse of the pH scale, so an acid with a low pH would have a high pOH. So, like, that does call back to an earlier diagram that I had drawn out. Okay, so if we have 0 here, and then 14 there, and then 7 right there. So remember that pH is correlated to hydronium, or hydronium ion concentration. So when you have a low pH, you have a large concentration of hydronium ions. However, when you have a basic solution, the concentration of hydronium is quite small. Conversely, with a basic solution, your concentration of hydroxide ions are going to be quite big, so that's why I'm drawing it big, whereas an acidic solution will have a small concentration of hydroxide ions, that's why I'm drawing it quite small. So how this statement here relates to this diagram here is because pOH correlates to the concentration of hydroxide ions. Okay, so as you'll see in our calculations with hydroxide ions there, if you have a small concentration of hydroxide ions, you are going to have a large or a high pOH, which is going to relate to a low pH. Okay, so just keep that in mind. It might seem a little bit fuzzy right now, but as you go through some calculations, it'll get a little bit more clear. Another way that we could draw out this diagram here, just relating to pH and pOH, actually, we'll go like that. Okay, so when you have an acidic solution, your pH is going to be quite small. So a very acidic solution would have a pH of, 0, 1, 2, something like that. Whereas a basic solution would have a big pH. So that's why I'm drawing it quite large. Okay, conversely, a solution that's basic would have a small pOH. But if it's acidic, it would have a large pOH. Okay, so this is the pOH and pH version of this diagram, just to make it a little bit more visual what this statement is saying here. Okay, so note the same significant digit rules apply to pOH and ion concentration as to pH, being the number of significant digits of concentration is equal to the number of decimal places of pOH. Okay, so with this, what it's saying here is that pOH has a P in it. So for sig digs, you look after the point, okay, which is something that we said in an earlier lesson there, okay. So this is why I was saying anything with a P in it, like pH or pOH, your sig digs are going to come after the point. Whereas for concentration, that word doesn't have the letter P in it, so you're going to look at the entire number to figure out how many sig digs you have. Alright, so example 1. What is the pOH of a solution with a hydroxide concentration of 1 times 10 to the negative 7 moles per liter? Okay, so remember hydroxide ion concentration directly correlates to pOH, so we don't need to do any additional calculations before we figure out what pOH is using this formula. Okay, so step 1, write out our formula. So negative log hydroxide ion concentration, which, as we said, is 1 times 10 to the negative 7. So if I put that in my calculator, so negative log 1 and then second function log to get that 10 to the power of negative 7. Click the right arrow over 1 and then close the bracket. Okay, that's going to give us a pH of 7. So this is neutral. Okay. Now, looking at this number here, since it's concentration, we're going to look at our whole number to tell us how many sig digs we have. And here it looks like we have 2 sig digs. So that means our final answer has to have 2 sig digs. Right now, it doesn't have any sig digs because there's no digits after the decimal point. So in order to keep the same value but increase the amount of sig digs, we just gotta put the decimal in and then add 2 zeros. So this is 2 sig digs here. Okay. Now, when we're talking about bases, which can be ionic compounds, some bases are going to dissociate in water to give you 1 hydroxide ion. So here we have sodium hydroxide, the dissociation equation for sodium hydroxide, and it gives us 1 sodium ion and 1 hydroxide ion. Now, because the coefficients in front of all of the products and reactants are the same, so they're all 1, the concentration of sodium hydroxide should be equal to the concentration of hydroxide. However, that's not always going to be the case. So for example, some bases like barium hydroxide yield double the amount of hydroxide ions when the compound dissociates. Thus, the concentration of the base itself and the concentration of hydroxide are going to be different. So here they've given us the dissociation equation for barium hydroxide. So when barium hydroxide dissociates, we get 1 barium ion and 2 hydroxide ions. Okay, so we're going to work on an example here, and I'm just going to adjust it just a little bit. So instead of 0.5, let's go 0.050 mole per liter. So let's say we have a concentration of barium hydroxide and it's at 0.050 mole per liter. Okay, so first let's figure out the concentration of hydroxide. So how we're going to do this is using our mole ratio. Okay, so as a reminder here, I'm going to have to write it up here because I don't have room lower down. Okay, our mole ratio is the coefficient. Is that how you spell coefficient? No. Here we go. Coefficient of what you want divided by the coefficient, which I'm just going to abbreviate to that, of what you're given. Okay, so this is a quick little reminder. This is something that we've done in the solutions unit when we were trying to figure out concentration of different ions. Okay, but this is our mole ratio. So because it's based off of coefficients, we need a balanced chemical reaction for it, which we already have. It's right here. Okay, so we are given the concentration of barium hydroxide. Now, if you're thinking to yourself, wait a second, barium hydroxide, according to my solubility table in my data booklet, it's not soluble in water. That's okay. If you're told in the question that it is, you just pretend that it is. Okay, so that's what we're going with. All right, so to figure out the concentration of hydroxide, what we're going to do is take the concentration of barium hydroxide, and then we're going to multiply it by our mole ratio. Okay, so when you're trying to figure out what our given and what our want is, our given is going to be barium hydroxide because that's what substance the number that we're given belongs to. Okay, and what we want is going to be the hydroxide ion concentration. Okay, so remember, we got to do coefficient of want divided by coefficient of given. So we want hydroxide. We are given barium hydroxide. Okay, so you can kind of treat the substances sort of like units. So these cancel out. And 2 times 0.05, that's going to give us 0.01 mole per liter of hydroxide ions. Okay, the reason why I'm not worrying about states too much here is because I'm not writing a chemical reaction, but you absolutely should include charge. Alright, so now that we have the concentration of hydroxide, we can move on to figuring out what the pOH is. The reason being why we had to figure out concentration of hydroxide first, it's because that's what our formula needs in order to figure out pOH. Okay, so let's write out our formula first. So negative log concentration of hydroxide is equal to negative log 0.1. So if I put that into my calculator here, so negative log 0.1, close the bracket, hit enter, that gives us a pOH of 1. Okay, now looking at our question here, this number right here has 2 significant digits because it's concentration, and we got to look at the whole number here. So leading zeros, they're not going to count for significant digits, but any digit that isn't 0 and trailing zeros are going to count for significant digits. Okay, so now we got to put this into 2 significant digits, which that's just going to mean that it's 1.00. Because for pOH, the digits after the decimal are what counts for sig-digs. Another reminder here is that pH, both pH and pOH do not have units. Okay, moving on. So next example, what is the pOH of a 0.0025 mole per liter solution of calcium hydroxide solution? So just because in this example we're given a little less of a head start, okay, rule of thumb is if you are given a substance in a question like this that is an ionic substance, first step is going to be to dissociate it. Alright, so let's write our dissociation equation first. So we got calcium hydroxide and remember, dissociation equations only produce two products, the cation, your positive ion, and your anion, so your negative ion. So first one I'm going to say is calcium, and then my anion is going to be our hydroxide ions. Okay, and at this point now I need to balance, so we have one calcium going in, one calcium coming out, two hydroxides going in, so we got to have two hydroxides coming out. Alright, so now that we have our balanced chemical equation, notice how we're given the concentration for calcium hydroxide. We are not given the concentration of hydroxide ions. So what we need to do is use our mole ratio to convert concentration of calcium hydroxide to concentration of hydroxide. So our mole ratio is want over given. We want hydroxide ion concentration. We are given calcium hydroxide. So these cancel out. And 0.0025 times by 2, that's going to give us 0.005 mole per liter. And this is of hydroxide ions, or our concentration of hydroxide ions. Alright, and then last but not least, now we can figure out pOH now that we have concentration of hydroxide ions. So negative log concentration of hydroxide is equal to negative log 0.005. And if I put that into my calculator here, so negative log 0.005, hit enter, we get 2.3010. And then the number keeps on going on forever. Okay, now looking at my given number here, this has 2 sig digs, so we got to make sure that our final answer has 2 sig digs. So remember, this is pOH, so you count your sig digs starting after the point, because pOH has a P in it, so 1, 2, there's our cutoff line, so then it's going to be 2.30 is our pOH. And again, no units because pOH does not have any units. So if you really wanted to label this as step 1, step 2, step 3, step 1 would be figure out your dissociation equation if the question gives you an ionic compound. Okay. If it does not give you an ionic compound, then what you would do is you would react the basic substance with water and do a modified Arrhenius reaction equation. Step 2, you need to figure out your concentration of hydroxide ions. Step 3, figure out pOH. There you go. Alright, next we're going to figure out how do we calculate concentration of hydroxide ions when we are given pOH. Same deal for when we were figuring out hydronium ion concentration from pH. Do not forget about this negative. It's very easy to forget. So if you're getting funky numbers, you probably forgot this negative here. Okay, so again, you can only figure out the concentration of hydroxide ions only if you have pOH. You cannot figure out concentration of hydroxide ions from pH. Likewise, you cannot figure out the concentration of hydronium ions from pOH, okay, or vice versa. So just a heads up, you can't mix and match. pOH correlates to concentration of hydroxide ions. pH corresponds with concentration of hydronium ions. Okay. So example here, what is the concentration of hydroxide ions of the below solutions with the following pOH? Alright, so first one we're given is a pOH of 2.5. So pOH, oh, hang on, hydroxide ion concentration is equal to 10 to the power of negative pOH. Now we plug in our numbers, so 10 to the power of negative 2.5, which if I plug that into my calculator, so I go second function log to get that 10 to the power of negative 2.5, hit enter, we get 0.003162, goes on forever. So 0.003162, blah blah blah, goes on forever. Okay, so if we're looking at our original number, there's only one sig dig here because this is pOH, so we look after the point. So that means our concentration value only has to have one sig dig, which is going to be this sig dig right here. So there's our cutoff line. So do I have enough room for this? Yep. So one sig dig, and we have 0.003, and remember concentration does have units, so we need to go mole per liter of hydroxide ions. And then put a box around it. Next we have a pOH of 5.422. Alright, so what you can do is you can pause the video and try these next two calculations by yourself because it's pretty similar to what we just did. Okay, so I'm going to give you time to pause the video and work ahead. Alright, so write out our formula first. Plug in our numbers. And then we're going to calculate it out. So second function log negative 5.422, enter. So 3.78, now I gotta look up that number, 44, keeps on going on forever, but it has a times 10 to the power of negative 6. Okay, so just a reminder that that E at the end of the number just means times 10 to the power of. Alright, so our given number, it has 3 sig digs. So that means our concentration value has to have 3 sig digs as well. So our sig digs are going to be 1, 2, 3 right there. So there's our cutoff line, and then I gotta scooch this over here. So 3 sig digs. So that's going to be 3.78. And then whatever you do, do not forget about the times 10 to the negative 6. People often forget about it. Remember, 3.78 times 10 to the negative 6 is not the same thing as 3.8. Those are two wildly different numbers. This one is way smaller compared to this one. Okay. Oop. Alright. And then also don't forget about your units. So moles per liter of hydroxide. Okay, last one here. Start off with our formula. And then plug that into my calculator here, negative 2.65. Boom. Okay, so 0.002238. Yeah. Okay. So looking at our original number, we have 2 sig digs. So our final answer also has to have 2 sig digs. So we're counting from here. There's our cutoff line. Remember, leading zeros do not count for sig digs. So then our value is 0.0022 mole per liter of hydroxide. Okay, so keep in mind if you also wanted to put this into scientific notation, you could do that. So if you wrote this number instead as 2.2 times 10 to the power of, so it'd be 1, 2, 3, times 10 to the power of negative 3 mole per liter of hydroxide. Both are right. The exponent here is negative because our original number is between 1 and 0. So that's why the exponent is negative, to just show that this number is a small number and not a big number. Because if the exponent was positive, that would mean it's a big number. So either or, both of these are right. Okay, so in this next part here, this is going to be what you can use to convert between pH and pOH. Okay, so this is a pretty important formula. Let's make sure we highlight it. So the whole purpose of this formula is that it allows you to convert between pH and pOH. Okay, because just as a reminder here, so I'm going to write this over here. So pH is used to find concentration of hydronium. How do you do that? By using this formula. So hydronium is equal to 10 to the power of negative pH. That's how you'd find that. Okay. Alternatively, if you had the concentration of hydronium ions and you wanted to find pH, how you would do that is you would go pH is equal to negative log concentration of hydronium ions. Okay, so what I'm trying to say here is pH helps you find concentration of hydronium ions. It does not help you find concentration of hydroxide ions. Okay. On the other side here, we have pOH. pOH helps you find concentration of hydroxide. And how we can find that is by using this formula. Is hydroxide ion concentration is equal to 10 to the power of negative pOH. Or if you wanted to go the other way around, so you're starting with concentration of hydroxide ions and you want to go and find pOH, how you would do that is you would go pOH is equal to negative log concentration of hydroxide. Okay? Again, what I'm trying to say here is pOH only helps you to find concentration of hydroxide ions. It does not help you find concentration of hydronium. Now, with this formula here, this is our bridge between pH and pOH. Okay, because sometimes you are given the concentration of hydroxide ions, but you are asked to find pH. So what you would have to do is you'd have to first find pOH and then find pH using this pH plus pOH is equal to 14 formula. Okay, so heads up on that. This is how all of these formulas are functioning together here. Okay. So example 1. What is the pH? So that's what we're trying to figure out of a solution that has a pOH of 3.4. Okay. So since we have pOH and we're trying to figure out what pH is, we are going to start off with pH plus pOH is equal to 14. Now, since we want to find pH, we're going to have to isolate that first. And how we're going to isolate that is by asking ourselves, okay, mathematically, what is pOH doing to pH? Well, it's adding. So the opposite of adding is going to be subtracting. So I'm going to subtract pOH, and what you do to one side, you have to do to the other side to keep everything equal. So pH is equal to 14 minus pOH. And now we just plug in our numbers. So 14 minus 3.4. So that is going to give us a pH of 10.6. And this value that I have for pH, it's already in the correct amount of sigdigs because we only have one sigdig for pOH, because remember, you only look after the point for pOH because it has a P in it. So then pH also has a P in it, so you only look after the point. So this is also one sigdig. So we're good to go on this front. And once again, no units are needed. All right, next example. What is the pOH of a solution? So that's what we're trying to find. What is pOH if we're given a solution with a pH of 12.22? Okay, so similar idea. Let's start out with our formula. It's equal to 14. So this time around, because we're asked what is the pOH, this is the thing we want to isolate. So mathematically, pH is adding to pOH, so we gotta subtract pH, and what we do to one side, we have to do to the other. So then pOH is equal to 14 minus pH. So then we got 14 minus 12.22, which is going to give us 1.78. And again, this already has the correct amount of sigdigs because this has 2 sigdigs, and so does this value here. It has 2 sigdigs because we are talking about pOH, so you only look after the point. All right, now for our challenge question. What is the concentration of hydroxide of a solution if it has a pH of 12? Okay, so we're looking for a concentration of hydroxide. We're given pH. Okay, so as a reminder here, we are looking for concentration of hydroxide. We are given pH. So first we need to figure out pOH using this formula here at the top so that we can then get to concentration of hydroxide ions using 10 to the power of negative pOH. That is going to be our game plan here. Alright, so since we're trying to find pOH, what I'm going to do is I'm just going to steal this formula that we figured out. So pOH is equal to 14 minus pH. 14 minus 12, that's going to be 2 for pOH. Now to figure out concentration of hydroxide, that's 10 to the power of negative pOH. So then it's 10 to the power of negative 2, which if I throw that into my calculator here, so that's second function log negative 2.01. And since this is concentration, that's moles per liter. And let's just double check sig digs. Okay, so this has 2 sig digs here. So we want to make sure that our answer has 2 sig digs there. So right now it only has 1 sig dig. So I'm just going to tack on another 0. And now it has 2 sig digs right there. So this is, oh, nope, that is not pOH. That's concentration of hydroxide. Okay, so just as a reminder, if you are given pH, you cannot directly find concentration of hydroxide ions. Okay, you first need to figure out pOH and then concentration of hydroxide ions.